Good morning, and thank you. I'd like to start by thanking the organizers for giving me this opportunity to present my work, which was done with my supervisor at CISA, Laura, and Kevin and Homa. Now, this title has several different parts to it, and throughout this talk, the idea is I'll try to break down each part and then hopefully finally put all the pieces together. So, but before that, let me start with why we started sort of looking at this work. Why did we even care about asking this question? So, initially, like around 10 years ago, when this entire story of the whole celestial holography program was being started, the soft theorems really played an important part in trying to understand what these conformal symmetries on the boundary, uh, how are they coming into the picture. So understanding the soft theorem is becomes really important from the point of having a more clearer understanding of the full celestial holography program. And these have been very well studied at the tree level, and the understanding has been developed pretty well, I can say. And we wanted to extend this to beyond just the tree level understanding. But even independent of this question, you can just ask this question to understand better the infrared structure of the gauge or the gravity theories. And even without it, you can just ask this as an independent question to understand what are the what are the symmetries of for a asymptotically flat space-time. Now, finally, this particular one that the subleading soft theorem that I'm going to be talking about today is related to the celestial stress tensor, which is the stress tensor for the proposed CCFT dual. So, in that context as well, it becomes important to understand what exactly this loop corrections are. Okay, now let me start with some historical background of what exactly the soft theorems are. So this story is a bit old. So the first time pointed out by Weinberg in 1965. So if you have a scattering amplitude with n plus one part, so m is the scattering amplitude with n external legs, which can be anything. This can be fermions, bosons, gauge bosons, anything. But you have one graviton whose momentum I'm parameterizing. Omega is the energy and q hat is the direction of the momentum, and pi is parameterizing the momentum of all the other external legs. And then you take the energy of this external graviton to be soft, which is you take the energy to be very small. In this limit, you can actually factorize this n plus 1 amplitudes in terms of a factor which depends on the external momentum and the graviton momentum, and multiplies only the n point amplitude without the gravitational um, insertion. And this is what we call here the soft theorem. And now that this expression you have written, of course, there are two small parameters in this expression. One is the omega, the external graviton energy, and other is the coupling constant in case of in here, which is the gravitational coupling constant. So you can ask for the expansion of this expression in both of these parameters. So you can have the amplitude expanded in the loop expansion, and you can also have the soft factor expanded in the soft factor. And these are the terms that we call the leading soft factor, the subleading soft factor, the sub-subleading soft factor, and so on. Okay. Now, the leading computation was also done by Weinberg in 1965, where he computed that the soft term is this epsilon here is the helicity of the external graviton, and these pi's are the momentum on all the other particles. And this factor that then you can, after you write down this factor, you can also then expand the other amplitudes in their loop expansion, and what you find that you can write this term exactly in all order. So here I've multiplied with this omega. What this do is this will extract this term, and when you take the limit, it will set all the others to zero. In that sense, you can say it's projecting out the leading soft factor, and then you can write this term order by order to perturbation theory, and this is the same no matter which loop you're computing. Secondly, the other feature about this S0 is that it is universal in the sense it does not depend also on what your external legs are. It could be fermions, bosons, gauge bosons, or spin particles, or massive or massless. Next, now this was already old, but after this recent, well, in the last 10 years, it was then studied to the next order in the omega expansion, which is the subleading soft factor. And we call it here the S1 tree. So, okay, I'm not giving the form of this S1 here because it's not that important, but the main thing is that when you write down, again, it in this projection like term, so here previously this omega was projecting out the S0 term. Here this function is projecting out the term that multiplies omega to the 0. And for tree level, you can again write down exactly this with what S1 tree was here. But now later, then when you start expanding this term in the loops on, so you can do a loop expansion of the n plus 1 point amplitude, and you can do a loop expansion of the n point amplitude, and you start to match what are the IR divergences on the two sides. And what these people found that to match the IR divergences on the left-hand side of this expression, you need to have an IR divergent correction to S1 itself, here called the S1 loop. And you see this is multiplied by an IR divergent factor 1 over epsilon. So when you write down the subleading soft theorem, which is exact to all loop orders in perturbation theory, you see that it is actually modified by a term. This S1 is a sum of S1 tree and S1 loop. Okay. Now this was this, yes. This is also independent of the external legs. Yes. In the sense that it does not depend on the external legs. Yes. No, I mean asymptotically flat gravity. Okay. Then this was this was the computation in 2014. Later, another computation was done, and this was really a brute force calculation by taking all the loop amplitudes at one loop and the tree level, and just computing this soft factor. So as I said, it's the factorization between this n plus 1 and the n point amplitude. This was done by Sahu and Se in this paper, and when they computed these amplitudes, n plus 1 tree level, loop level, they computed n point amplitudes, tree level, 1 loop level. They took this limit, and what they found is that there is no infrared divergent correction to S1 tree, but there's a term that comes with a log omega soft factor. That is what we call the SLN here. And this, as you can see, this log omega is more leading than omega to the 0. And this only comes at one loop. So with this soft factor, you can now write the subleading soft theorem with this projector as the log omega factor plus the subleading soft factor. Yes. No, they don't miss. That does not appear here. Yeah, I'll explain it. So, okay, first so this SLN is really going to be the star of this talk. So let me show you what it looks. It seems to be. I'll resolve it. That's the first question. Yes. So let me show you what this SLN looks like in its full glory, because so this is some kinematic factor that again depends on the external legs and the graviton momentum. But okay, here it looks a bit ugly. So okay, and now I'm going to comment on both these questions, that what's the apparent mismatch. So the reason is that what they found was actually the same factor. So if you go and do the computation, you look at the results. So this is SLN is nothing but S1 loop. They suggest is that in the sense what Byrne et al. Computed was they asked how to get the infrared mismatch on the right hand side from an infrared term infrared mismatch on the left hand side from an infrared divergent term on the right hand side. So this means what this explicit computation suggests, that this infrared divergence term is really this log omega, and to match both the two results, you really have to identify this 1 over epsilon with this log omega factor. Okay. So R is some infrared cutoff you have to put in, because you have, so in physical sense, it could be, for example, the distance of your detector. Yes. Yeah, like diagram, the Feynman diagram. Yeah, sure. Okay. This is, for example, the leading term. You can have any legs here. Now for the subleading term, similarly, and you multiply. Oh yeah, this is, and yes. So this wiggly line is the graviton. These external lines can be anything. Similarly, okay, thank you. Yes, this loop. I mean, this loop can be anything. The loop momentum is running over all the momentum. Okay. Yeah. So this one, yeah, this will give no contribution to, yeah. Okay. Right. So then, okay, now that we have to discuss about this factor, so first let's write down this in a more compact form, which is manageable. So we define this. This is again, one can check in both these papers to match that this is defined in terms of these kinematical functions sigma, which are, so sigma n here is the function that depends on all the external momentum, and sigma prime is when you take one of these external momentum and replace it with q hat. So, and this S0 and S1 tree are as before. Now there are two terms, and I want to emphasize a bit on this, that the first term here actually comes from the interaction due to external soft particle with the loop. So for example, okay, did not draw it here, so this would be something like this. And so, okay, I'm not going to say much about QED, but just one line. So if in QED also this log factor could be computed, but since this comes from interaction of external soft with the loop, then this is the term that would be absent in QED. That's all I'm going to say about QED today. Now, the second term, Yang-Mills is also a bit more complicated, just not, so in Yang-Mills also the leading soft factor receives loop correction. It's a bit different story there. Yes, I'm sorry. By Yang-Mills, I mean when the external particle is a soft gluon and not a soft graviton. Yeah, thank you. So, when it's an external particle is a soft graviton, then it does not depend on the theory. Um, and then there's this second term, which comes due to the interaction, which comes due to these kind of interactions where you have external, just the external hard particles with the loop. Okay. Now there's one more subtlety here which I've not mentioned, is that there's a real and an imaginary part to these functions. And this is not going to play much role on what I'm going to say to the rest of the slides, but towards the end I'm going to comment on it again. Right. So at this point, I can ask the main question for this talk, that can we understand these logarithmic corrections as coming from superrotation word identities? Now, why do we expect it, and what are these superrotation word identities? That is what I'm going to talk about next. So before that, any other questions from the previous part? Okay, thank you. So now for the asymptotic symmetries, these are the asymptotic symmetries of asymptotically flat spacetime, and I'm sure this is you've seen this a lot of times. So so here we're just expanding the metric in a Bondi flat coordinate, and when you write down the metric expansion and ask what are the fields diffeomorphisms that preserve this asymptotic fall off, you these guys found these functions, and here these t's are functions over the sphere which parameterize supertranslations. These y's are holomorphic and anti-holomorphic functions which parameterize superrotations in the sense of Barnich and Sosov. And this is what we here call the BMS symmetries. This is just a bunch of equations to set up some notations. Now, in this metric, there are some functions that are fixed by the Einstein's equation of motion, and there are some other functions which are free. And this free data at Scri plus, they will parameterize the radiative phase space at this null infinity. Right. Now, this phase space can we can separate it into a hard and a soft part. And by hard and soft here, simply mean that the hard part is defined over the entire Scri, while the soft part is defined on a section of Scri plus. So this, okay, there are some new notations here. So this CZZ was the same that appears in the metric here. So it's the shear. This NZZ is the news defined as the time derivative of the shear. You have the anti-holomorphic part for both of them. Then you have the matter sector. This is, so here these fields only correspond to the gravitational data, but additionally you can also have matter data that also comes in the hard phase space. In the soft one, you have this C0 mode, which is made out of the boundary value of the shear, so Scri plus plus and Scri minus plus minus. Then you define the integration of the news and with this curly ends, and you can define without taking a power of u and with one power of u, and these give you two different fields. And additionally, just for sake of completion, I've also mentioned these two fields, but we are not going to be, they are not going to be important. Finally, this C0 here, which is made out of the boundary data for the shear, is the Goldstone mode of supertranslation, in the sense that under supertranslation, this transforms linearly. Now that we have the transformations, we can find out how these fields transform, and these are the phase space. So we can ask what are the fluxes that will make these canonical transformations on the phase space, and this was computed in this paper. So like most of these expressions are in terms of the phase space variables that I just showed you. There are two new things about this slide. So first is this T2. This T is really the matter stress tensor. So it's the stress tensor for the matter fields that you have in the bulk that you can have additionally other than the gravitational data. And the second part is that I want to emphasize here is that this Fy soft, this can be split into two parts. So this first part was already computed in this paper, and I'll show you what this was in a second. And then there was the second part which was found by asking what are the canonical transformations. So here I call it the F soft, like here they call it the F soft 0 and the F soft nu. So the Yeah, so these are really going to be the BMS fluxes that we are going to now ask for the for the word identities on the on the space. So any question from that part? Okay, now that we have the two different pieces, so we can put them together. So how do we incorporate for that? So that comes from asking for the word identities of this fluxes. So first of all, to know the word identities of this fluxes, we must know what are the mode expansions. To find out the mode expansion of the shear, we can compare it with the linearized metric, and this HZZ is just the graviton. So if you put in the mode expansion of graviton field here, you can find out what the mode expansion of the shear is. Once you know the mode expansion of the shear, you can go back here and you can see that you can compute all the other mode expansions from the shear. Now that you know the mode expansion and now that you have these symmetries, you can start asking for the word identities. So the invariance of the S matrix under supertranslation means that the S matrix commutes with the supertranslation flux. So you write down the full flux, there's a soft part and then there's the hard part. This is just the expression. So if you would write down the commutator, everything would be on the left hand side. I've just split it and then taken the hard part on the right hand side. Now you have this expression, you plug in these forms, you plug in the mode expansion, and what you find surprisingly is exactly these leading soft theorems. Right, so this was the story at the leading order. In fact, the fact that they're universal is related to the fact that they're related with this super translation symmetry. As I was telling you all along that the story at the subleading order is a bit more tricky. So, but before that, let's go to the older story at the subleading order. So this is what I was talking about with Fy soft 0. So you can already sort of compute the word identity with just Fy soft 0. And when you plug everything here, the mode expansion, the form of this term, you get just you already get the tree level subleading soft theorem, right? But the tree level term, we know that this is not the full term. We have a correction coming because of the loop. So we really have to account for this full subleading soft theorem from somehow this superrotation flux. Hmm. No, it's not enough, the global part. This factorization. Yeah, I'm sorry, but I don't have the understanding of higher space-time dimensions. Maybe what? Okay, this might be one answer, that maybe in higher dimension these S1s are not universal, and if they are not universal, you don't really expect them to be coming from some symmetry. But I'm not sure about that. So no. So log omega term only appears in 4 space-time dimension. In higher space-time dimensions, you don't have any infrared divergences. You don't have any log omegas. Okay. So right, so now we have we want to recover this full term, and here just to remind you, this first term comes from the soft loop interaction, and the second term comes from like the hard loop interactions. Right. So let's see how do we do that. So first remember that here already we had a Fy soft new term. We can already ask, okay, what is the correction because of that? Now, before that, here, okay, in all of this term, there was fields whose mode expansion you could have calculated directly from here, from this graviton field, except this C0 that now appears in the FI soft new, which also recall was given in terms of this goldstone mode. You can also compute the insertion of this goldstone mode in the S matrix, and this was done here. And you find this result. This sigma prime is again is the same sigma prime. And now using this, you can then compute what is the insertion of Fi soft new, and you find this the first term in the SLN. This is the term that was coming because of the interaction of the external soft particle with the loop. So it makes sense that the term coming from the correction of a soft flux gives you, from the loop point of view, the term coming from the interaction of the external soft particle with the loop. But we are still left with the hard part, and if we follow similar logic, we would now expect the term coming, the second term coming from the correction for a hard flux. So let's go to the hard flux now. Now, this hard flux can be written in a more convenient form in terms of this T mu nu is the matter stress tensor, and this xi is as before the diffeomorphism field. Now, if you take this T mu nu, you put in the free fields phi, you put in the formula T mu nu equals del mu phi plus eta mu nu del phi squared. You compute T mu nu, you take the limit to Scri plus, and you get exactly the term which also appeared here. Let me go back to this term here. You are already getting just from a computation of asking for the free fields in the bulk. But we know that the bulk fields are not free and they interact with gravity, and these gravitational interactions are long range. So they will have some effect when you take the limit of these fields going to Scri, and these effects can be captured by replacing these free field creation operators with these dressed field creation operators. And here the dressing, the C0 is the goldstone mode of super translation as before. So if you now, instead of the free field stress tensor, you compute this interacting field stress tensor, then you get this part as before, but then you also get an additional part to it. So this is what the delta Fy hard here is. And now in the word identity, you will also have this part, and then you have to ask, okay, what are the corrections due to that part? And as I anticipated already, this gives you exactly the term which comes, the term in the soft, the loop corrected soft factor, which comes due to the interaction of the external particles with the loop. Yes. Everything is fine. No, there is no correction. So so you are saying that if here if I compute it with the dressed fields, right? Yes. Right. Yeah, yeah. No, at leading order, everything is unchanged. Please? No, I mean, at leading order, you can replace the mode, but then you find out and then there is no correction to the leading order. Yes, yes. Yes. Exactly, exactly. Okay, thank you. So then, okay, now when we put this additional factor here, we get the second term of this the logarithmic soft theorem, and now we can really write the full word identity with all four terms. And what we find is with this full fluxes inserted in this word identity, you reproduce the full subleading soft theorem. Okay, now this was this was the main result of this work, but in the yes, sorry, yeah. Okay, I'm sorry. So This was the main result, but in the path to obtaining this, we observed two more interesting things. So first, I talked to you in length that the one loop infrared divergent loop correction and the subleading subleading soft theorem and the logarithmic soft theorems are equivalent, seen as sort of two different regularization schemes. The second thing which I commented a bit about, but we didn't get into the detail, is that the infrared factorization of amplitude contains a real and an imaginary part. Now, this infrared factorization was shown earlier to be reconstructed out of the two-point function of the Goldstone mode. That construction only contains the real part. To also account for the imaginary part, you have to modify the two-point function of the Goldstone mode by this imaginary factor. And finally, if you take all of these things in account, you modify your um, your subleading soft flux, your superrotation soft flux, your full superrotation flux. You can account for the subleading soft theorem as I showed. Okay, but that is not the end of the story. There's not just one subleading soft theorem. There's an entire sort of pyramid of these theorems. You have at tree level, at loop level, at each loop you have a different soft factor appearing. And there are a lot of interesting questions that one can ask out of it. Here I'll leave you with some of them on the top of my mind. So thank you.